Hi everyone, let us discuss Gauss Divergence Theorem. So this theorem says the surface integral is equal to this volume integral. Okay. So what have they given? We have a region, solid region in R3V, and the boundary surface of that region V is S. So let us consider this object in R3. So it's this object, the complete volume is denoted by V, or the complete solid region is denoted by V, and it has some surface, so we denote it by S. So we have a vector field F. So they are given F is equal to Pi plus Qj plus Rk. So these are the component functions of capital F. So if you have a function like this and a PQR must have continuous partial derivatives, then the double integration f bar dot n cap ds over that surface S, okay, that surface of that object is equal to volume integral over the volume of that object divergence of v bar dv. So we have to prove that both of them are equal. So let us write what we have to prove exactly. So let me mention here, to prove that double integration over S a bar dot n cap ds is equal to triple integration over v divergence of a bar dv. Okay, so we have the value of f or f bar, you can say, that is pi plus qj plus rk. So let us put its value here. So therefore, or that is to prove that double integration over s pi plus qj plus rk dot n cap ds. So here also on ijk also you can write cap. Okay, so this is equal to triple integration over v. Divergence means you know del dot f bar is, okay, I will write f bar dv as it is. So still we haven't started proof, simply we are discussing what we are going to prove exactly. Okay, so that is to prove that, let us simplify it more. Double integration over s, that is you can take a dot product separately. So pi dot n cap plus qj dot n cap plus rk dot n cap ds is equal to triple integration over v. So you know that del means what? Del means dabba by dabba x I plus j dabba by dabba y plus k dabba by dabba z dot f bar, that is nothing but pi plus qj plus rk dv. So this is equal to triple integration over v. So you know well how to take a dot product. Multiple of I into multiple of I, that means if you take a dot product you will have dabba p by dabba x plus multiple of j into multiple of j dabba q by dabba y plus dabba r by dabba z dv. Okay, so this thing we have to prove. So you know that if addition is there, you can take separate integration for double integration also and for triple integration also. So yes, let me write here, we have some space, let us use, let me mention, that is to prove that double integration over s pi dot n cap ds plus double integration over s qj dot n cap ds plus double integration over s rk dot n cap ds. Okay, so in the right hand side also addition is there, we can take separate triple integration. So triple integration over v dabba p by dabba x dv plus integration dabba q by dabba y dv plus integration dabba r by dabba z dv. So you can easily see in left hand side we have 3 double integrations and in right hand side we have 3 triple integrations. So now it is enough to prove that the first surface integral is equal to first triple integration, second double integration is equal to second triple integration, and third double integration is equal to third triple integration. Okay, so let me write that thing also, make a screenshot of it, then I will go further. So that is to prove that double integration over s pi dot n cap ds is equal to triple integration over v dabba p by dabba x dv and double integration over s qj dot n cap ds is equal to triple integration over v delta q by delta y dv and double integration over s rk dot n cap ds is equal to triple integration over v delta r by delta z dv. So simply we have to prove that these three equalities. Okay, so out of these three we will work on only one equality. So here we are going to prove last equality. This double integration is equal to that triple integration, and similarly we will say the first two will hold. Getting? So at the end we are going to add them and we will have the required answer. Okay, so this thing we are going to do. So let us focus on this last equality only. So we are going to prove this triple integration is equal to this double integration. Okay, so now what will I do? I am going to define the given region V in this way. Okay, so let me mention let V is equal to, so it's see, we have a region in R3, so we should mention in this way XYZ belongs to R3 such that XY belongs to D, getting, as and f of xy less than or equal to z less than or equal to g of xy. Okay, so in this way we have defined V. So let me tell you what I have done exactly. So we have a region like this, we have some region in R3, getting? So yes, let me show here. So we have such type of region in R3. So as you can see, at the top of this region we have some function, so I am calling it as z is equal to g of xy, getting? And at the bottom we have some surface, so I am calling it as, its equation is z is equal to f of xy. So its projection in xy plane will be some like this, so that is nothing but D. So its projection in xy plane is D. So yes, so V is bounded above by this z is equal to g of xy, that region V is bounded below by z is equal to f of xy. So in this way we have defined this region V, getting? So let us start to work on, let me mention here D is a projection of V in xy plane. Okay, so its projection in xy plane, it is bounded above by z is equal to g of xy, bounded below by z is equal to f of xy. So what is our target? Our target is to prove this equality. We are going to prove this triple integration is equal to this double integration. So let us start to work on this triple integration. So let us consider triple integration over V delta r by delta z. So dv is there, so you know that dv means dx dy dz, or you can consider dz dy dx. So here dz and dy dx we have, I am denoting it by d. Okay, so I am considering first z. So yes, so let me write first dv, and in next step I will do this. So dv is equal to triple integration delta r by delta z dz, and after that dA means dy dx or dx dy, getting? So first we are integrating with respect to z, so I should write the limits of z. So here we have defined this region in this way, so you can easily see that z is bounded above by g and z is bounded below by f. So the upper limit of this integration is g of xy and the lower limit will be f of xy, getting? F of xy. Yes, so by solving this integration, still we have a double integration, so obviously it is defined on region D, which will be the projection, right? So in this way we are going to solve. So for this case we can use the first fundamental theorem of calculus, getting? But see, I will solve step by step. So let me write here. So this is equal to double integration over D. So what will happen here, we are differentiating with respect to z as well as we are integrating with respect to z. So derivative and integration will get cancelled to each other and we will have simply r x y z with upper limit g of xy and lower limit f of xy, and still d is there, getting? So this is equal to double integration over d. So you know that after integration, first we put upper limit and then we put a lower limit. So this is the limit of z, these are limits of z. So let me put upper limit first, xy g of xy minus, I am putting lower limit at a place of z, r xy f of xy. So So this is f, okay, f of xy ds. So by solving the right hand side we got this one. See, actually we never write this step directly by first fundamental theorem of calculus. We get this step from this one, getting? So here also you can mention clearly by first fundamental theorem of calculus. Okay, that's it. So I'm calling it as equation number 1. So we work on the right hand side and we got its value. So let us work on this left hand side also. Okay, so there is no more space to write. Make a screenshot of it, then I will go further. So let us try to find the value of that surface integral. Okay, so let us talk about surface integral. So here, so you know that S is a surface of that region, getting? So S is made up of 3 surfaces here. Let me mention here, S is made up of 3 surfaces. See the first S1. So S1 is bottom surface. That means at the bottom of this region we have some surface. So I'm calling it as S1, getting? S2, that means top surface, and S3 is that vertical surface. Let me show it here. So this is S1. At the top we have a surface, that is S2, and this is the vertical surface S3. So if you consider this object, obviously it is made up of 3 surfaces. At the top we have one surface, that is S2. At the bottom we have one surface, that is S1, and this is a vertical surface, that is S3. In some cases there will not be S3. If you have a sphere, there is no any vertical surface, getting? So no need to consider S3, but in general we can divide this surface S in 3 parts, S1, S2 and S3. Then we can write, then double integration over S, we were talking about that Rk dot n cap ds. Okay, so we are finding the value of third equality. Okay, left hand side of third equality. So this is left hand side of third equality, right? So S is made up of 3 surfaces. So I should mention double integration over S1 plus double integration over S2 plus double integration over S3. That means we will find values of all these separately, and at the end we will add. So we will have the value of this left hand side. Okay, so let us talk about S3 first. So for S3, S3 means that vertical surface. Let us consider this object. So this is S3, okay, vertical surface is S3. So what will be the n cap? N cap means normal vector, getting? N cap is normal vector. So the n cap will be like this. But as you know, K, yes, where is it? K. So this is, you know, x axis, this is y axis, and this is z axis. Along x axis we have a vector I. Along y-axis we have a vector z, and along z-axis we have a vector k. So that means k is vertical vector, okay, in the direction of positive z-axis. So our k is like this, and n cap is a normal vector which will be like this. So let me show here. So n cap will be like this and k will be like this. So if you consider n cap at any point, definitely it will be perpendicular to that k. So here let me mention, so here for S3, n cap and k are perpendicular to each other. So you know that if two vectors are perpendicular, their dot product will be 0. So therefore k dot n cap, or here also you can write cap, is equal to 0. So therefore double integration over S3 we are finding Rk dot n cap ds, but see their dot product is 0, so the value will be 0, getting? So the value of this double integration is 0. So let us talk about S1 and S2 now. Make a screenshot of it, then I will go further. So now we will find the value of surface integral over S2, okay, so over S2. So where is our S2? At the top we have a S2, okay. So let me draw the surface like this so you can easily understand. So this type of surface we have, okay, S2. So S2, that means at the top we have that surface. So you can easily see its equation is z is equal to g of xy. So here we are going to follow our regular method. In problems also we follow the same method to find the value of surface integral. The same method I am going to use. So to find the value of surface integral, we need to have a parameterization. So let us find a parameterization of S2 now. So let me mention parameterization is I will denote it by phi of xy. So you know that in parameterization we try to express the surface in terms of two variables only. So let me write here x, y, and the last variable is z. But for S2, what is the equation of S2? Z is equal to g of xy. So I can write here g of xy. So you know well how to find the value of surface integral. So for that we need to find parameterization, then cross product of phi x and phi y. So all these things I am going to do now. So let us find derivative of phi with respect to x. So it is 1, 0, derivative of g with respect to h, gx, right? Phi y, derivative of phi with respect to y, 0, 1, and derivative of g with respect to y. Getting? So after that we want the value of cross product. So phi x cross phi y. So you know well how to find the value of cross product by solving a determinant. First row is obviously ijk, phi x having components 1, 0, gx, right? And phi y having components 0, 1, gy. So you know well how to find the value of determinant. Okay, so for determinant what we do? I, product of this two, 0 minus 1 into gx, you will have gx minus z. For middle term always we write a minus sign. Product of this two, gy and minus 0 plus k, 1 minus 0. So it is minus gx minus gy and 1. So we got a cross product. So let us find the value of that f of phi of xy. Okay. So here let me mention first here f. See, f is the actual vector field, but see for this double integration I will call it as f1, that is rk. What is the field we have? Rk for that double integration, getting? So rk, that means 0, 0, r. Getting my point? See, there is no any I, so that's why its multiple is 0. There is no any j, so that's why its multiple is 0. Only we have a k, last component, so I am writing in this way. So this is our r. So therefore, f1 of phi of xy is equal to, so the first component is 0, no need to worry about it. Second is also 0. So here we will have r phi of xy. It means 0, 0, r phi of xy. What is it? Phi of xy is xy g of xy, right? Okay, so in this way we got its value. So let us go further. Then we take a dot product. What is dot product? So f1 phi of xy dot phi x cross phi y. You are getting my point? I am following the same method which we use to solve the problems. Okay, for a surface integral we have a perfect definition, so that definition I am using. So phi of xy, it is this one. Phi x cross phi y, is this one. So we are going to take the dot product. So you know well how to find the value of dot product. First component into first component. So 0 into anything 0, right? 0 into anything 0, and this r into 1 you will have r. So that means this is nothing but r of xy g of xy. So there, so let us find the value. Double integration over S2 we are finding rk dot n cap ds. So this is equal to double integration over d. I am saying d because as you can see, so this S2 has a projection in xy plane is d. Projection in xy plane is d. So that parameterization is defined on domain d. So that's why I should consider d. You are getting my point? So S2, that surface S2 has a projection in xy plane is d. So the parameterization is also defined on domain d. Yes, so the definition says, that is, let me write f1 phi of xy dot phi x cross phi y dx dy, or simply you can write dA. So this is the definition of surface integral of a vector field, right? But the value of this dot product we have already calculated. Its value is this r of xy g of xy. So let me write it here. Double integration over d r xy g of xy and dA. That's it. So double integration over S2 also we have got. So just before it we proved that double integration over S3 is 0, double integration over S2 is this one. So let us talk about surface S1 now. Okay, make a screenshot of it, then I will go further. So let us talk about S1 now. Okay, so S1 means a bottom surface, getting bottom surface. S2 is a top surface and S1 is a bottom surface. So what is the equation of S1? That is z of f of xy, getting. So actually the projection of S2 and the projection of S1 is same, that is D, getting. Simply S2 is at top and S1 is at bottom. This is the only difference. So here I can mention for S1 n cap is in downward direction, okay. What it means, so you can consider this object, this is S2 and this is S1. So for S2 our normal vector will be like this, but for S1 the normal vector will be like this. So it will have exactly opposite direction. For S2 it is in upward direction and for S1 it is in downward direction, getting. So S n cap is in downward direction. So therefore I can directly write double integration over S1 Rk dot n cap ds is equal to double integration over D. As I told you earlier, the projection of S2 and projection of S1 is same, which is D, getting. So I can write D. I am writing directly. Actually you can perform all these steps and you finally will have the same answer. So D R xy, f of xy should mention, getting, since the equation of S1 is f of xy, that normal vector is in opposite direction, so that's why I should write minus sign and dA. So directly I wrote the value of double integration over S1. So we got the values of all three double integrations, so surface integral. So let us add. Then surface integral over S, f bar, see, we were finding the value of Rk dot n cap ds. This is equal to double integration over S1 over S2 and over S3. So what is value of first surface integral? It is minus double integration over D R xy f of xy, right, dA. The value of second surface integral is this one, plus double integration over D R xy g of xy dA, and the value of third one is 0. So here we can take that double integration common, dA common. So this is equal to, I can write double integration over D. So it has a positive sign, it has minus negative sign. So R xy g of xy, right, minus R xy f of xy. Okay, so it has a minus sign, so that's why I consider it second, and it has a plus sign, so that's why I consider it first, dA. So this value we got. See, I am calling it as equation number 2. So you remember in equation 1 also we had got same double integration. So in equation 1 and equation 2 we got same right hand side. So that's why you can say the left hand sides are also same. Make a screenshot of it, then I will go further. So let us combine 1 and 2. Let us see what we will get. So from 1 and 2. So 1 and 2 having a same right hand side. So left hand sides are also equal. Double integration over S Rk dot n cap ds is equal to triple integration over V dava r by dava z dv. Okay, so you remember initially we stated 3 equalities, getting, and out of these 3 we proved the 1. So similarly we can write the remaining 2. So similarly double integration over S pi dot n cap ds is equal to triple integration over V dava p by dava x dv and double integration over S qj dot n cap ds is equal to triple integration over V dava q by dava y dv. So if you add all these 3 equations, if you add all these 3, you will have double integration over S f bar dot n cap ds is equal to triple integration over V divergence of f bar dv. at the beginning of this proof we have already discussed by adding all this how will you get this one. So I can directly write, so this double integral, or you can say the surface integral, is equal to volume integral. Okay, so in this way we proved Gauss divergence theorem. Make a screenshot of it, then we will stop. See you.